Okay, for the next module, we're going to be looking at stoichiometry, which is quantitative information about chemical reactions. So we're going to begin with mass relationships in chemical reactions, which is stoichiometry. And we want to understand the principle of conservation of matter, which forms the basis of chemical stoichiometry, calculate the mass of one reactant or product in a reaction, knowing the balanced equation and the mass of another reactant or product in that reaction, and use amount tables to organize chemical information. Okay, the following skills are going to be required to do these stoichiometric calculations. You need to be able to balance equations. You must understand that coefficients can represent mole ratios of reactants and products in a perfect reaction. You must be able to convert between grams and moles of a substance using the molar mass of the substance. You must be able to calculate the molar mass of a substance given the formula. And you must be able to convert between moles of one substance in a reaction to moles of another substance in the reaction. So, balancing, we've already covered this. You do adjust coefficients, and you do not change the formulas for substances, and you use the law of the conservation of mass or matter. Okay, coefficients. Here's a balanced reaction between aluminum hydroxide and sulfuric acid. And the coefficients are 2, 3, 6, and 1 respectively. We need to understand that these coefficients can represent moles of substances rather than just numbers of molecules or formula units. So for stoichiometry, we like to think of this as being 2 moles of aluminum react with 3 moles of sulfuric acid to make 6 moles of H2O and 1 mole of aluminum sulfate. And if we want to convert between moles of substances, we simply use these mole ratios. So for instance, if we had X moles of H2SO4, and we could pretend that this number is 2 just for argument's sake, and we want to get moles of H2O, we would multiply by 6 mole of H2O to 3 mole of sulfuric acid. So we get these numbers here from the balanced reaction. And remember, I said we're going to pretend this is 2. So if we start with 2 moles, we'd end up with 2 times 2, or 4 moles of H2O. So we use these molar coefficients when we convert between moles of one substance and another from a balanced reaction. Here we have molar mass. So this is the same reaction. Quick reminder, to get the molar mass of a substance, you ignore the coefficient and you simply look at the elements in the compound. In this compound, there's 1 aluminum. There are 3 OHs, which means there's 3 hydrogens and 3 oxygens. And to get the molar mass of this material, we get 78.004 grams. Converting from grams to moles, you start off with grams and you multiply by the molar mass, where the grams is in the bottom and the moles is in the top, so that things cancel. And here, if X happened to be 78 grams, or let's say if X happened to be 156 grams, if we plugged it into this formula, we'd end up with 2 moles of aluminum hydroxide. Converting from moles to grams, you start off with moles of a substance, and you multiply by the molar mass, where the mass is in the numerator and the moles is in the denominator, so that these cancel. And here, if Y happened to be 2 moles of H2O, we'd end up with 36.04 moles of H2O. The pathway for stoichiometric calculations is as follows. So here, if we take a look, this is the reaction. And let's say that we start off with 1.23 grams of aluminum hydroxide and we wanted to get grams of H2O. Here's the pathway. We would take the grams of aluminum hydroxide and we would calculate the moles of aluminum hydroxide. and we'd use the molar mass of aluminum hydroxide to do that. If we wanted to then get the moles of H2O, we would use coefficients from the balanced reaction. And finally, we could take the moles of H2O and convert that into grams of H2O using the molar mass of H2O. So this looks like it's 1, 2, 3 problems, but it's not. It's one problem with 3 conversions. And that's the way I want you to do it on an exam. Not 3 separate problems. You will not get full credit. Okay, so let's take a look at this example. Calculate the grams of water formed by the reaction of 1.23 grams of aluminum hydroxide. So here's the pathway. And this pathway here is the same as this one right here, only I've written it linearly instead of this box shape. So we're going to start with aluminum hydroxide, convert it into moles of aluminum hydroxide, convert that to moles of H2O, and then to grams of H2O. In this pathway up here, each arrow is an arrow down here. So let's call that arrow 1, arrow 2, arrow 3, arrow 1, arrow 2, arrow 3. And each one of those arrows, 1, 2, and 3, 1, 2, and 3, each one of those arrows, we're going to use a conversion factor. So if we start off with 1.23 grams of aluminum hydroxide, we're going to multiply by the molar mass of aluminum hydroxide. So we know that 1 mole of aluminum hydroxide weighs 78.00 grams. I put the 78.00 grams in the denominator so that these grams and grams will cancel. That means the mole has to go into the numerator. Next, so that's conversion 1. Conversion 2, I'm going from moles to moles, and I want to use the balanced reaction. So I see that there are 2 moles of aluminum hydroxide to 6 moles of H2O. So I'm going to put the 2 moles of aluminum hydroxide in the denominator so that these things cancel. And I'm going to put the 6 mole of H2O in the numerator because I want to convert eventually to grams of H2O. So this is the second one. And lastly, I'm going to use the molar mass of H2O, which happens to be 18.02 grams of H2O. Now look at this molar mass compared to this molar mass. This one I'm using upside down compared to the previous one. And why am I doing that? Well, because I want the units to cancel. I got mole of H2O, mole of H2O. And then we just plug the numbers in. And here we have to understand that these mole coefficients are exact. They have infinite numbers of figs. Here I have 3. Here I have 4, infinity, 4, infinity. So I end up with 3 significant figures, 0.852 grams. And so does 0.852 grams seem like the right number given what we have here? Well, we could say, well, 18 will go into 78 about 4 times, right? And 4 times 2 is 8. 1.23 times 6 is going to be a little bit more than 6, maybe 7 or something like that. So a 7 divided by 8 going to be really close to 1. And the answer is yeah. So I believe this answer. Now you'll notice that I have written labels with all of my number and unit. Imagine what this would look like without all the labels. If I didn't have aluminum hydroxide here, if I didn't have aluminum hydroxide here and aluminum hydroxide here, if I didn't have H2O and aluminum hydroxide here, just let me cover that one up. Suppose I didn't use labels there and I had 6 mole over 2 mole. Who would think 6 mole is equal to 2 mole? No one. It doesn't make sense. But 6 mole of H2O equal to 2 mole of aluminum hydroxide in a reaction. Can reactants and products have different coefficients? Absolutely. So the units are nice, but you also need the labels. Not only the units, but the labels. So this is how you do a stoichiometric calculation. So let's do some examples. Now, this is a good opportunity for you to read this, pause it, give it a try yourself, and then see what happens when I do it. So I'm going to pretend that you've read this, you paused it, and you've gone ahead and solved it, and you're going to see how I do it compared to the way you've done it. Now, what I'm trying to instruct you here is what you would be expected to show on the exam. So glucose, C6H12O6, reacts with oxygen to give CO2 and H2O. What mass of oxygen is required to completely react with 25 grams of glucose, 25.0 grams? What masses of carbon dioxide and water are formed? Okay, so I have a blank sheet of paper underneath here, and I'm going to give you some of how I would do this. But first, I'm going to give you a little background here. You see this C6H12O6? It can be rewritten this way, C6H2O6. And you can see that here there are 6 carbons, 12 hydrogens, 2 times 6, 12 hydrogens, 6 oxygens, and 6 oxygens. This is a carbon, and we learned about hydrates previously. This is a carbon hydrate. And when you put it together, you get hydrate. So you've all heard the term carbohydrate. The origin of the carbohydrate is that many sugars have a ratio of 1 carbon to 1 H2O. Okay, so the first thing we need here is we need a balanced reaction. So we're going to put C6H12O6. And for this, we're not going to worry about the states because there's nothing in here that says, well, what are the states? Now, when you react this with oxygen, it is O2, not O, because oxygen is a binary molecular compound. Or I should say, binary element. Now, we're going to get CO2 plus H2O. So now we balance. So, how many carbons? 6. How many carbons? Now there are 6. How many hydrogens? 12. How many hydrogens? 2. If I put a 6 here, now there are 12 hydrogens. How many oxygens here? 6. How many here? 8. So we have 8 total over here. How many on this side? 6 times 2 is 12. Plus 6 more is 18. We need 18 over here. We already have 6 here, which means what? Well, 18 minus 6 is 12. I need 12 more oxygens. And if I put a 6 here, I can get 12 more oxygens. So here's the balanced reaction. Another thing that would be nice to know is the molar mass of all of these things, because we're probably going to end up needing it. So when we have a C6H12O6, that's going to be 6 times 12.01 grams, 12 times 1.008 grams, and 6 times 16.00 grams. So I'm doing this in my head, so it's going to be a little slow. 6 times 12 is what? 72.06 grams. 12 times 1.008 is going to be 12 grams. And then 12 times 8 is what? 80 plus 16, 96. And 6 times 16 is going to be 96.00 grams. So when we do the gram total here, we get a 6, a 5, a 1, a 0, carry the 1, and we get a 18. Now, CO2 and H2O and O2 are a lot easier. O2, we get 16.00 grams times 2, which is 32.00 grams. H2O is 18.02 grams, and CO2 is 44.01 grams. I'll let you work those out for yourself. So these are the molar masses, and we don't really need this as part of our work, but it's kind of nice to have it over here to the side. You can see I didn't show any work for these two, and hopefully I got them right. Otherwise, it's going to mess up my problem over here, and you can't get full credit if you don't get the correct answer. Okay, so the first question is, What mass of oxygen is required to completely react with 25 grams of glucose? So I'm going to take my 25.0 grams of glucose, and here I'm going to put G for glucose because I don't want to write this formula out. I'm going to turn that into moles of glucose, turn that into moles of O2, and turn that into grams of O2. So that's the pathway. And I could stretch this out and make it linear, but I'm going to start off with 24.0 grams of glucose and multiply by 1 mole of glucose per 180.16 grams of glucose. So I went ahead and rounded that off, is because this really is only good to the 100th. And when I round that to the 100th, I get 5 zig figs. Here I have 3 significant figures. And when I have 5 zig figs, that's not going to affect the outcome. So I don't need to carry that extra digit around over here. And then here, I want to use the balanced reaction. So we're talking about oxygen. There are 6 mole of O2 to 1 mole of glucose. And lastly, we want to use the molar mass of oxygen. And there's 32.0 grams of O2 per 1 mole of O2. And when I look at this and try to estimate the answer, I realize that 6 will go into 180 probably, what, 30 times? And 32 divided by 30 should be about 1. So the answer should be around 25 grams, okay? A little bit more, because I think that this is 30 into 32 is a little bit more than 1. So a little bit more than 1 is going to be a little bit more than 25. So I'm going to turn on my calculator. I'm going to clear it. I'm going to put 25 times 6 times 32 divided by 180.16 and equal. And we get, I'm going to change this to flow. We get 26.64 grams, 26.6 grams of O2. And there's our answer. So for a problem like this, where you're not given a balanced reaction, I would expect you to write out the balanced reaction, and I would expect to see this. And I would expect each of your molar masses to be correct, and I'd expect to see the correct number of significant figures. Okay, what masses of carbon dioxide and water are formed in grams? So we could do the same thing for the mass of carbon dioxide in grams. And when I say the same thing, I mean the same type of calculation as this, except when we get to here, we're not going to do 1 mole of glucose to 1 mole of carbon or oxygen. We'll do 1 mole of glucose to 6 moles of CO2. So we're going to start off with our 25.0 grams of glucose times 1 mole of glucose per 180.16 grams of glucose times 6 mole of CO2 to 1 mole of glucose times 44.01 grams of CO2 to 1 mole of CO2. And in this case, I can also estimate the answer in that if you take a look at this, with this 44 compared to this 32, this is about 1.3 of these. So my answer should be about 1/3 bigger than this. So 1/3 of this is probably about 8. So 8 plus that, the answer should be around 32 or 33. So let's take a look. 25 times 6 times 44.01 divided by 180.16 is equal to 36.6 grams of CO2. So I would expect to see this also for part of the problem. Now, how about the mass of O2? We can get it one of 2 ways. Here's one way to do it. 25.0 grams of glucose times 1 mole of glucose per 180.16 grams of glucose times 6 mole of O2 to 1 mole of glucose times 32.0 grams of O2 per 1 mole of O2. And here you can see that this, oh wait, we've already done the O2, haven't we? We need to do the H2O, my bad. So I'm going to cross this off and cross this off, and we're going to put mass of H2O. And what we're going to have here, instead of 6 mole of O2, is we're going to have 6 mole of H2O to 1 mole of glucose and 18.01 grams of H2O to 1 mole of H2O. So here, if we compare this to this above, this is about half of that. So this answer should be about half of that. A little bit more, because 18 is a little more than half of 32. Okay, so for my calculator, I've got 25 times 6 times 18.01 divided by 180.16. Now, another way we could do this is 18 will go into 180 10 times. 10 will go into 25 2.5 times, and 2.5 times 6 would be 2 times 6 is 12, half of 6 is 3, so that'd be 15. So the answer should be around 15. Okay, so let's see what we get. 15. 15.0 grams of H2O. So this is the kind of work I'd expect to see for all of this problem, but there is another way to get the mass of H2O. Now, we know that there's 25 grams of glucose, and for the oxygen, we know there's 26.6 grams, and for CO2, we know there's 36.6 grams. So based on this, we know that the sum of these two numbers has to equal the sum of this plus the mass of H2O. So another way to get the mass of H2O would be to take the mass of glucose plus the mass of O2 and subtract from that the mass of CO2. So in this case, we would have 25.0 grams plus 26.6 grams minus 36.6 grams. And let's try this in the calculator, see if it works out or if I made some mistake along the way. And we get 15. Okay. Now, why is this also good to the 10th? And the answer is because that's good to the 10th, that's good to the 10th, and that's good to the 10th. So either way, we get 15 grams of H2O. Okay, so that's some stoichiometry. Let's take a look at another problem. Oh, this is the one we just looked at. Let's look at another stoichiometry problem. The reaction of iron 3 oxide with aluminum to give molten iron is known as the thermite reaction. It gives off a lot of energy. So we take this iron oxide, this is called iron 3 oxide, and you react it with aluminum, and you get iron, and you get aluminum oxide. Now this is a redox reaction, and we can tell very easily because we have pure aluminum on this side, and we have aluminum in a reactant or in a product on the other side, I should say, compound. So whenever you go from a pure element to an element in a compound, that's a redox. And it works backwards too. If you go from an element in a compound to the pure element, it's a redox. So this gives you a great hint that this is a redox reaction. Okay, what amount of aluminum in moles is needed for the complete reaction of 3 moles of iron 3 oxide? And what mass of iron in grams can be produced? So let me rewrite the reaction. So we have Fe2O3 plus 2 aluminum gives you 2 Fe plus Al2O3. You'll notice I've left the states off, and the reason I've left the states off is they kind of get in the way and we're not asked about the states. So the first thing we're asked, what amount of aluminum in moles is needed for 3.0 moles of Fe2O3. So for this one, we can simply go directly from the moles of Fe2O3 to the moles of aluminum. So the deal here is that we're going to start with 3.0 moles of Fe2O3, and we're going to multiply by something that has moles of Fe2O3 in the bottom and moles of aluminum in top. So where do we find those mole ratios? The answer is coefficients of your balanced reaction. So if this is balanced, then we're going to put 1 mole here and 2 mole here. So let's double check and make sure that the book gave us a balanced reaction. 2 irons, 2 irons, 3 oxygens, 3 oxygens, 2 aluminum, 2 aluminum. So here's the solution for what amount, and we would end up with what? 6.0 mole of aluminum. Remember, coefficients are exact, so they have an infinite number of significant figures. Now, they also ask us in this problem, what mass of iron in grams can be produced? What mass of iron in grams? And presumably, it's from 3.0 moles of Fe2O3. Okay? So we're told that we're mixing 3.0 moles of this, 6.0 moles of this, and we're asked how many grams of iron. So can you see that we could start with 3.0 moles of Fe2O3 and convert that into grams, convert that into moles of iron, and then convert that into grams of iron. We don't need to convert this into grams, which is what I was about to do. Once you have the moles of a substance, you can convert it into moles of the other substance using the balanced reaction. So this should get us our answer. But remember, in this reaction, we're mixing this much and this much together. So that means we could also start with 6 moles of aluminum, turn that into moles of iron, and turn that into grams of iron, and presumably get the same answer. So let's find out if we do. So here is the solution for this part. 3.0 mole of iron 3 oxide times 2 mole of iron to 1 mole of iron 3 oxide, and then times, and I need the molar mass of iron, which is 55.85 grams. And if we look at the answer, you can see that we're going to have 3 times 2 is 6, 6 times 55 is 330-ish, maybe 340-ish. So let's do the work. 3 times 2 times 55.85, and we get 335 grams of iron. Now, that's too many significant figures for this, right? So it should really be 340 grams of iron, because I want to keep the first 3. I want to keep the second 3, but I have to look at the number to the right to see if I round that 3 up or down. And I want to round it up because that's a 5. Now let's try this. 6.0 mole of aluminum times 2 mole of iron to 2 mole of aluminum times 55.85 grams of iron per 1 mole of iron. And you can see that 6 times 1 is the same as 3 times 2, so we're going to get the same answer. So this would be the perfect reaction if we had exactly 3 moles of iron 3 oxide and exactly 6 moles of aluminum and reacted them, and if everything worked perfectly. Okay, so that's that problem. Let's look at another stoichiometry problem. Like many metals, aluminum reacts with a halogen to give a metal halide. 2 aluminum, or 2 mole of aluminum, reacts with 3 mole of bromine to give you 1 mole of aluminum bromide. Okay. Now, in this case, this is also a redox reaction. Notice we have pure aluminum here, and it's in a compound over here, redox. And if we didn't notice that, we should notice that there's pure bromine here, and bromine is in a compound here. That's a redox. So we're asked, what mass of Br2 in grams is required for the complete reaction of 2.56 grams of aluminum? So what I'm going to do here is I'm going to start with my 2.56 grams of aluminum. I'm going to make the box this time. Turn that into moles of aluminum. And we're asked what mass of Br2 in grams. So we're going to turn that into moles of Br2 and turn that into grams of Br2. Now to do this, we're going to need the molar mass of aluminum, which is 26.98 grams. We're going to need the molar mass of Br2, which is going to be 2 times 79.90. So 79.90 times 2, and I get 159.8 grams. And we need to know the mole ratio, which apparently is 2 to 3. So if I make this pathway linear, which is what I really like to do, I'm going to start with 2.56 grams of aluminum, turn that into moles of aluminum, turn that into moles of bromine, and turn that into grams of bromine. And I should be able to figure out how many grams of bromine we need to react with the aluminum. So 2.56, this is a good time to push pause if you haven't finished it yet. 1 mole of aluminum for 26.98 grams of aluminum. Why did I put 26.98 grams of aluminum on the bottom? If you said to cancel the units, absolutely correct. Okay. Why did I put 2 moles of aluminum on the bottom? If you said to cancel units, you're absolutely correct. Okay. Now, what goes on the bottom over here? 1 mole of Br2 and 159.8 grams of Br2 on the top. And so if we estimate the answer here, 26, I think of that as being like a quarter, right? 25, a quarter is 25. Let's pretend this is a quarter, and this is going to be $1.50. How many times will a quarter go into $1.50? 6 times. What is 6 times 3? 18. 18 divided by 2, 9. 2.56 times 9, well, that should be 9 times 9, 9 plus 9 plus half of 9. So that puts you at roughly 23. So we expect an answer around 23. So 2.56 times 3 times 159.8 divided by 26.98 divided by 2, and I get 22.74. And it looks like we get 3 significant figures. So 22.7 grams of Br2. So that's your answer. Now, I don't expect to see this here, but I do expect to see this as part of your answer. And I don't expect to see this here or this here as part of your answer. So that is the grams of Br2. What about the mass of aluminum bromide? Well, there are two ways of getting that number. We could do this. 2.56 grams of aluminum, turn that into moles of aluminum, turn that into moles not of Br2, but turn that into moles of aluminum bromide, and then turn that into grams of aluminum bromide. Now, what we're going to need here is the molar mass of aluminum bromide, which is 26.98 grams times 2 plus 79.90 grams times 6, which is a big number. So this is one way to do it. What's another way to do it? Well, another way to do it would be this. Let's see, we have 2.56 grams of aluminum, plus we have 22.7 grams of bromine. I don't want to put that there. And so the total mass here is, let's see, plus 2.56. The total mass is 25.3 grams. Well, according to the law of the conservation of matter, if we start off with 25.3 grams, we should end up with 25.3 grams. So I'm going to leave it to you to discover if we do get 25.3 grams using this method. Okay, that's it for this first section of this particular module. Hope you enjoyed. And if you didn't enjoy, I hope you learned something.